Our first speaker this morning is Abhi Shelat, a leading researcher in cryptography and secure computation, currently at Northeastern University and Google. Abhi's research has been at the forefront of multi-party computation and privacy-preserving protocols, innovations that are becoming central to the next generation of digital systems. His talk today, The Modern Credential, will explore how we rethink identity and verification for a decentralized world. Please join me in welcoming Abhi Shelat.
Thank you, Suprit, for the introduction. The Modern Credential. This is joint work with my colleague Matteo Frigo, and this is like a painting that I think captures this idea of a anonymous credential. You don't see the face of the piano player, but you do recognize it's a person has the identity attribute of playing the piano. It's this artist Wilhelm Hammershøi. So this is Erica's credential, and she doesn't want to carry around this plastic card anymore. And she also does not want to upload pictures of it to assert any attributes about herself. And this is a not just a theoretical concern here. Like I found these type of things on all sorts of forums. People do not appreciate sending uploads of their of their identity, of their physical identity document, in order to satisfy some sort of assertion about their identity. And this person, for example, hesitant to give a photocopy of my ID to companies, and you know that once you upload those things, it also becomes a hassle for the company to properly store this and keep it and log it and make sure that it doesn't get breached. And KYC processes, which is, it should be a topic. I think it's a topic in the conference here. This is kind of how KYC is done today. So how can that be improved? Well, enter the digital credential. So this is the idea that after some ceremony, an issuer, like most notably a government, can sort of send a signed document to your device. And this is done in a private way. So even like the company that facilitates the transfer of the information, like, so for example, if you're using Google Wallet doesn't actually get any of your private data. The protocol is encrypted end to end from the issuer, the government, to your device. Now, what can you do with the digital credential on your phone? Most notably, you can present that digital credential. So Erica can use her digital credential to present either in person or online some selected attributes from their identity. And in this talk, we're going to focus on the online case, but same sort of principles apply for the in-person or real-world identity cases. Now, the important privacy feature of this entire area of digital credentials is selective disclosure. And this idea has been explored in the cryptographic literature since 1985, with anonymous credentials, Chom introducing those ideas, and many, many papers in the literature talking about that concept. The modern version of this, it started at least in 2016 with this ISO working group. As far as I looked into their documents here to see when this work started, very early, they included this note, which is there must be some requirements for selective release, including, for example, the age verification use case. So right when they started this work, there were no cryptographers involved, but they understood the need for privacy and in the sense of selective disclosure. So what they came up with is this legacy ISO MDOC identity protocol. And this is a protocol that's been deployed in practice and it's used today. And this is how it works. So if you informally want to state this blue claim here that the state of California, for example, has produced a signature on some document, this document is stored on my cell phone, and that document includes some attribute age over 18 is true. The way it works today is the relying party or website makes the request. That's the first message over here. I request the attribute I want to see and some transcript of this transcript. I'll talk about why we need this in a little bit. And then the response is essentially the full MDOC and a pre-image, some other information. So let me explain exactly what this information is in the next slides. And once the RP gets all of that information, they essentially go over this 5-step process to verify that information. So let's dig in. This is what an actual MDOC today looks like. this is a mobile driving license object. This is kind of the data parsed, and this is the data that's signed by essentially the issuer. And there are two parts I've highlighted here, what's called the salted hash, which is an attribute in the credential, and then this yellow part, a device-bound public key, which I'll talk about in a second. Okay, so in essence, this green part right here is essentially the hash, the SHA-256 hash of this red string. And if you look at this red string, essentially it includes a random salt here, this gray part right here, that you can see, as well as this blue part, which is the age over 18 encoded in ASCII here, as well as its value true, which in this particular encoding F5 stands for true. So essentially, uh, in order to disclose your age over 18 part, what you do is you send over this full MDoc, this entire document, which this example document includes 35 attributes here. But most of the attributes all of the attributes are these salted hashes, okay? And for the attributes that you want to reveal, you give this red string, which is essentially a pre-image of the salted hash. And so, in fact, the status quo flow is that the relying party makes a request, and you send over the full MDoc, as well as the pre-image for the attributes that you want to reveal, as well as the signature of this transcript part. So let me explain why you need to do that. So one of the key concerns when you're dealing with digital credentials is this attack where essentially someone copies the credential off of another person's phone. If it's easy to root a device, for example, then it would be easy to take this information, extract it from your phone, and put it on someone else's. And if this happens, it really undermines the soundness of the entire system, because then essentially anybody can claim any attribute, and there really isn't any meaning to the presentation process. So in order to prevent that, the people that designed this ISO protocol, again, I give them a lot of credit because they did this with no cryptographers involved. They essentially decided to bind a credential to essentially trusted hardware on the user's device. And this process is called device binding. And what that means is, if you look at a modern phone today, it involves several stacks here. At the lowest level, there's what's called a secure element, a piece of hardware on your phone that can store secret keys, can sign things, and has been purposefully designed so that it's difficult to extract the key from that piece of hardware. So that's at the hardware level. On top of that, there's an OS abstraction layer. On Android, it's called Strongbox. And then on top of that, there's an application level layer, like a wallet, can essentially make calls to Strongbox, which makes calls to the secure element and then essentially produces hardware bound signatures. And that, in fact, is what this yellow part of the credential is. So this is a device bound key. This is the public key that corresponds to a secret key that is on the user's device that's in the secure element of that user's device. And so when you onboard, and this is like an example of how this works, I'll show this little video here. This is how Google Wallet works. You agree to a bunch of things. When you onboard, you scan your existing driver's license and you upload it to the DMV. And that's encrypted end to end. So it's directly encrypted all the way to the DMV. And then you take this selfie video, which basically it randomly asks you to look up or look in one of the directions. You have to turn your head there. And it takes a live video of this particular process. And then once you do that, it takes the selfie video, uploads it to the issuer. The issuer verifies that, in fact, the person in the video corresponds to the person that that the DMV has a record of. They have your picture. In addition, this process basically asks the secure element to produce a key, to attest to the creation of that key, and to include the public key in that upload message. And so if the issuer decides that the video corresponds to the person, then it includes the public key that came along into this formatted message right here, and then it signs that message and then sends it right back to the device, encrypted end to end. Okay, so in fact, that's how the current system works. And in fact, changing any of these type of layers of this thing and doing anything different than kind of what is already, the pieces that are there that I've showed you, requires a lot of time to change the ecosystem. Okay, but unfortunately, okay, fine. So let me summarize exactly how this whole process works. So the relying party asks for the attribute that they care about, as well as this freshness, nonce. They want to prevent a replay from being performed. And they also want to make sure that essentially it's the device onto which a credential was initially um, sent and provisioned. That's the same device that is used to actually give this response. And so the response includes that full MDoc, the pre-image of the attributes that have been requested, as well as the signature of this fresh message that's fresh for this session using the device public key. So in other words, this last part ensures that the device onto which the credential was issued is involved in the presentation of the credential. And of course, at the end of this, the relying party needs to verify the signature on the MDoc. It needs to verify the signature on the transcript. It needs to parse the MDoc. It needs to find the pre-image. It needs to verify that the red string that's provided is equal to that pre-image. It also needs to check some dates to make sure that, for example, the time of the current time, basically, the credential is valid during that particular expiration period. Now, although this protocol solves the idea of selective disclosure and solves the idea of um, copying credentials by insisting on device binding, it in fact introduces a very deep and serious privacy problem. Okay, and that's unlinkability. And the attack is like this: if a user uses the same credential at relying party 1 and relying party 2, on account of the fact that they both have the same device public key in them, as well as the same salted attributes for them, then these two service providers or relying parties would be able to essentially link every session. So they would basically be able to combine all of their logs and tell all of the people that came to both of their websites. And they might use that for some other sort of unauthorized activity, like basically tracking users. Now, one of the ideas is that maybe maybe the user uses a different credential, like, so essentially they get 1,000 credentials issued to them when they sign up, and they use a different one for each website that they visit. That would solve the RP collusion problem, but it would in fact not solve the critical problem, which is that the issuer themselves would know exactly which device public keys belong to which particular user, and they would therefore be able to link. They would basically be able to link which users went to which relying parties. And that's a problem, because then that means the government can essentially track which users have used their credentials on which websites. Any questions about that so far? Is everything working as expected and so forth? Okay, great. So this is a legacy protocol. It's issued, it works today, okay? And it has a privacy problem. And the main point of my talk is that the modern credential, with the sort of cryptography that I'm going to talk about the rest of the talk in, that can solve all of these privacy problems. So essentially, the modern credential is a legacy, whatever legacy protocol has been deployed or is currently used, that sort of works with current user phones and works with issuers, hardware, etc. If you put a ZK NARC, and notice it's not a snark, it's a NARC, I'll talk about that in a second, then you can essentially build a zero knowledge that can gracefully deploy on top of any general protocol and essentially harden these legacy protocols so that they are essentially the golden standard. They meet the golden standard of user privacy. And that solution is simply you keep that first message that the relying party sends, and then instead of sending all of that information before, you send a ZK proof that all of these 5 checks that the verifier would have done would have been accepted. So you give a proof along with the time and the current transcript, which essentially, and the proof basically proves all of those 5 steps would sacrifice. Now, notice I mentioned that it's a NARC instead of a SNARK. So there are a few changes to the problem constraints that this is a slightly different than the classic blockchain and classic cryptographic literature. So succinctness is a key part of the blockchain because, of course, in that model, the verifier is a very small computer. It's essentially the node of the blockchain. In our model, it's the opposite. The prover is your cell phone. So it's a very small prover. And the verifier is essentially a very large website. So the tables are turned, and we actually are optimizing for prover time and resources instead of focusing on succinctness. And that, of course, gives us a little bit more flexibility in our design space. We also think that it's going to be very hard to have trusted parameters. So if you think about 50 states in the United States or 27 EU member states or 187 countries in this world, and if you want some sort of level of interoperability, I think it'd be very difficult for all of these organizations to come together and agree on a common reference string. That's just a matter of practical difficulty. And so we don't think that common reference string setups can scale, and thus we look for a ZK system that does not require a common reference string. And that, of course, rules out many of the schemes that rely on pairings and that are produce very, very short, like constant size proofs. We also don't ignore all of the work that people have done on all of these credentials. So these are just some of the working groups that have produced these things. The cryptographic literature, of course, has a solution for this, has several solutions, but they ignore all of these things that people have done. They also require, the hardware on your phone to do certain things that like support bilinear pairings and so forth that they currently can't support. And of course, finally, the solutions we think are practical do not involve the issuer doing O of internet activity work. So the issuer cannot be involved in the online flow. They can't even be involved in the offline flow. They can't be requested to do the amount of work that's proportional to the number of logins that people do. So in particular, we don't think it's feasible for the issuers to give every user a credential, a different credential for every website that they log into. And that's just because these hardware HSM modules are expensive and it's difficult to deploy and so forth. Many organizations we talked to require post-quantum security and thus didn't want things like bilinear pairings used in the ZK system, even if the signature itself used elliptic curves. And just to point out, the prior work didn't really work. Prior work on this essentially did not lead to a practical solution that could work on the phone. And my claim, in fact, the point of this talk is that the right ZK snark can solve all of these problems. And if you look at essentially the possible approaches that you could use to building a zero knowledge system that would be efficient enough to make a statement like this blue statement, there are, of course, schemes that require pairing friendly curves like BBS Plus and Groth16. But again, both of those has problems for deployments. Like in particular, BBS doesn't really have a clean idea solution for device binding. There's some papers on this, but none of them are really acceptable solutions. That leaves all of these other schemes that require only hash functions to provide zero knowledge. So that's right there a very positive aspect. It only requires like SHA-256. They're in the so-called IOP model. And there was Stark, Laharo, and this prior work of mine that was this called Hyrax. And that, in fact, turns out for these type of problems, turns out to be much more efficient than other solutions, and in fact, more efficient than ZKVM solutions. And it turns out to be the right, in our opinion, the right solution for the scales, for problems of this type of scale. And more specifically, what exactly is the ZK system that we're proposing to use? It's based on the oldest recipe, the second oldest recipe for ZK. So here, to build a ZK system from this paper right here in 1988, the paper was titled "Everything Provable is Provable in Zero Knowledge." You essentially take any interactive protocol that you have for the circuit that you want to prove, use that to produce a transcript, commit to the transcript, and then give a zero knowledge proof that the commitment contains this transcript and the IP verifier would have accepted this transcript. So to apply this recipe, you just have to pick these three components. And that's what we did. For the interactive protocol, we use this notion of a layered sum check protocol that's based on this work of GKR. And for the commitment and zero knowledge part, we actually use Laharo. And we use Laharo to, in fact, prove a statement about this interactive protocol. And the reason we picked Laharo instead of some of the other schemes that were possible, it was very fast. turns out you didn't need this recursion. You don't need this polylogarithmic size proof. A square root size proof, which is what Ligero supports, is fine. And it only uses the SHA-256 hash function. So to give you a sense of how our protocol works, essentially you first commit to essentially the original witness along with some sort of pad. You run a sum check between the prover and the verifier, except when the sum check sends a normal message MI, instead of sending that message MI, you send MI XOR this pad. So this is kind of sending a committed transcript of this sum check protocol. And then finally, you use the Ligero proof system for that with respect to this commitment. Essentially, this encrypted transcript would essentially verify under the original IP verifier. So that's kind of the high level overview of this protocol. And you might ask why, for example, do we do this, why do we use Ligero to prove something about an IP instead of, for example, just using Ligero? And the key idea there is that every other transparent argument of knowledge here, like Ligero or like Starkware, essentially they take the transcript of the circuit's execution, and in particular, every multiplication gate of the circuit, and they commit to it. And so your commitment is roughly the size of the circuit. And commitments, essentially in these IOP models, they are the most expensive. They're Reed-Solomon encoding of all of this data, and Reed-Solomon is an n log n process. In contrast, the sum check protocol right here, it runs in linear time in the size of the circuit. And so in particular, when you apply Ligero to this layered sum check, all you do is you end up in committing to the input, i.e. the witness of this particular circuit, as well as a very small pad that you use to essentially commit to the interactive protocol. You don't end up committing to all of the intermediate wires. And that leads to a much smaller, 50 times smaller commitment, and thus a significant improvement in the performance of the entire ZK system. So to give you a sense of that, let's consider the problem of verifying an ECDSA signature, which we can do with this very simple program right here, okay? But right away, we get to a problem. All of the prior work that runs into the same problem. Essentially, if you need to, all of the prior work for verifying an ECDSA signature, they needed to emulate the mathematics of FP, the prime that you use to define the ECDSA curve. You had to emulate that with respect to another finite field. And that's because nobody knew exactly how to produce this number, and nobody really had an efficient way of producing Reed-Solomon encodings on the field that's used for P256. And that's because if you look at the P256 finite field, this is its P-1 factorization. It essentially doesn't have the roots of unity that you need in order to commit, that you need to run like an FFT algorithm. We found a very simple solution to this particular thing. And in forthcoming work, we have an even better solution to this. You can use a quadratic extension, and then that one definitely has enough roots of unity. So you can, in fact, do a proof about verifying ECDSA signatures natively in the field of P256. But the point I was making is that doing our approach is significantly faster than just using Ligero. And with respect to that, if you look at the size of our circuit, okay, the number of inputs to that circuit is only 1,000 inputs. The number of arithmetic terms or multiplications in that circuit is about 50,000. And so here you can sort of see that using our approach requires committing to about 50 times fewer number of wires than a scheme like Ligero would. And that leads to, essentially in our original work, in our original paper, we sort of gave a zero knowledge proof of possession of a signature for ECDSA on a message and for a public key. We produced that in about 60 milliseconds. And subsequently, we've significantly improved the performance of that, and we can sort of do it in about 16 milliseconds now. And that's really, really close to essentially how much, I mean, that's very close to within the time it takes for any other sort of anonymous credential type of signature, like, for example, BBS and so forth. Similarly, to prove zero knowledge of the preimage of SHA-256, it takes about 11 milliseconds in our scheme. And if you use Lahero to do the same work, it takes about 273 milliseconds. So it's about 26 times more time than our own implementation. And again, this follows just because of this diagram right here. We just commit to less information than Lahero does. And that leads to a significant improvement in our thing. Where does that put us with respect to the original problem right here, which is how do you how do you build the modern credential? Well, essentially, remember, instead of having the RP send this information and you send all this information back, we need to send a zero knowledge proof for this last message in these 5 steps. And if you want to formalize that, essentially, you want to get a zero knowledge proof with respect to a public key of the issuer, the attribute that you care about, the transcript, and the time. These are the public parts of the statement. You want to prove that there exists a private witness that's, let's say, a 2200 byte document, a hash, another hash, an index, a signature, a nonce, a public key, et cetera, et cetera, et cetera, such that all of these statements below hold. Namely, that you have a signature under the issuer's key of essentially a mobile a driver's license document. If you parse that mobile driver's license document, it has an age over 18 attribute, and the nonce that that red string essentially produces that hash. Okay, so that same green hash essentially can be produced with the pre-image that you know. There's a device public key in that same credential, and you have a signature of under that device public key of the liveness, the transcript part, and of course the credential time period is about valid. Our circuit for this statement, for this group of statements, takes about 7 million wires. 3 million of those are quads. We have a specific form. 600,000 of them are in the field for ECDSA, and essentially 6.7 million, or about 90% of them, are in a binary field. And altogether, like this was a short demo of how this works, but I'm going to skip that for time here. This basically works in less than a second, about 800 milliseconds on a Pixel and about 300 milliseconds on an iPhone. So it works in less than a time. So every time you use this device, of course, because it involves a secure element, a user has to put their sort of either face scan or their thumbprint on the phone, and that time makes the whole process on the order of seconds. The computational aspect of the zero knowledge are only in the hundreds of milliseconds. Now, I think I only have about 5 minutes left. Is that correct? Okay, so I want to leave time for questions. Now, I just want to give you an idea. I have a lot more material. We've worked out how to do revocation, how to do pseudonyms, how to hide the set of issuers. So, for example, if you want to hide which of the 50 states, US states, your driver's license is from, or which of the 27 EU states, this comes from, or which nation you come from, we can handle other formats instead of MDoc. We can also handle JSON web tokens or JOTs. So I have a lot of more material about how we can do that. I also have some information about how Longfellow ZK works itself, and some information about how this scheme. So let me just quickly get to the back here. Um, how it works with ISO, with different formats, and why our schemes are better than other basic approaches to this type of thing. But I want to leave time for questions. So feel free to ask if what you want to hear about, or if you have any questions about how this works. I guess my final point there is that this technique is very generic. It can basically be used to augment any existing deployed legacy identity credential format to have this privacy, this full privacy, no linkability, and it's performant, it's deployable, it works with today's hardware and today's cell phones. It doesn't require any issuer to change anything about their process. In other words, it's a graceful way to augment the current ecosystem with privacy. That's why we call it the modern credential. Instead of requiring everybody to change to new crypto, we just require the wallet and the RP to essentially implement these two libraries on top of what they currently do. Questions?
Hi Abby, it's Nigel here. How are you? You hear me? Hello?
I can hear you, yes?
Okay, cool, right. So two questions. So the compiler, which is basically GKR plus Ligero, this could apply to any ZK statement. So, I mean, it would seem, so this would seem to be the way to apply Ligero in practice. Is that true? And then the second question is, you're using GKR. Now, my vague recollection is GKR has this attack in quotes if the circuit's too big due to Rothblum. Is that a problem here?
Okay, great. So two questions. First one is this the right way to deploy Ligero? So for these small problems, yes, Ligero has some other advantages in the sense that you can stream the computation. If memory, for very large statements, if memory is your concern, then the IP mechanism, the what you call GKR, that of course does require to kind of keep the entire transcript in memory. You can stream it too, but then it sort of you get into you no longer have a linear time prover. It becomes n log n, and so it's not clear that for very large statements this is the right way to do it. For all statements that I say are less than about 100 million gates, then I think this is probably the right way. So in fact, I think for things like MLDSA, for like quantum, for post-quantum signatures and so forth, if you want to basically just take any off-the-shelf PQ signature and add ZK to it, I do think this would be the right work, and this is what we're doing. Now, the second question you ask is about GKR. One thing I want to point out about it, I don't use GKR because so GCAR gives it's kind of the same way I called like garbled circuits. Yao's garbled circuit. That's like an initial. Nobody uses the garbled circuit that Yao proposed, right? The double encryption and so forth. It's the same sort of thing with GKR. The exact protocol in that paper is like nobody would use. There are a number of changes. Like for example, we don't even use arithmetic circuits. All those pictures in arithmetic circuit, we use what's called quadratic forms, and there are a number of other changes that make this system like and for example like most people who are doing this like Justin Thaler and Jolt and so forth, they're using a number of other techniques to speed up. It's not just the plus and multiplication. It's not the arithmetization that GKR says. But your question is about what about Ron Rothblum's Fiat Shamir attack on these type of protocols? And in fact, the simplest way to like we're aware of that attack, and it does not apply to this protocol or any of the real deployed protocols that are based on that technique. And that is because nobody who uses this layered sum check technique actually computes a function. We verify the function, and we do that in low depth. So we basically slice the circuit and we make it a very low depth computation that's too small for you. So that attack that Ron points out, essentially, it uses the protocol to compute essentially the random oracle response. And so in particular, it has to be as deep as the random oracle function. And I put some caveats into that. You can sort of do these tricks, but ultimately, the way to get around those type of attacks heuristically is just to make sure that the Fiat Shamir oracle that you use is way larger and way deeper than the functions that you're verifying. And so our circuits are about depth 16. And we, for example, our Fiat Shamir oracle, the first thing it does is it hashes a number of zeros that's equal to the number of gates in the circuit. So it hashes 7 million zeros, immediately making it sort of infeasible to kind of predict that output. Now I say that with caveats. Of course, if exactly what I said is not right, you have to be very careful with the order in which you do this. We've had Elon essentially, we've had several people look at our implementation and make sure that it's like not susceptible, and using best practices to make sure it can't that attack does not work. And of course, these are all heuristics. We don't have a correlation intractability argument for the exact function, but we've done our best there. I hope that answers your question, Nigel.
Thank you.
Hello? Oh, there we are. Hi, thank you for the fantastic talk. And I just wanted to follow up on some more practical elements. I'm not familiar with the MDoc wallets. Are those widely deployed in California as yet? And if so, is your improvement to these widely available, or how would we, let's say I'm interested in deploying some of your solutions, whether here in Singapore or otherwise in Asia, how could we follow up to get some of these proposals that you've put out here?
Great question. So here, let me show you this. The answer to it is that yes, you can. So this is now, it is being deployed and rolled out in Google Wallet. I'm showing you a demo here. Hopefully you can see this video. It's between a browser on your computer and your phone. And your phone has this, essentially this driver's license here. Let's see if, oh, I can't very easily pause this. Let's see if I can. Okay, so now that I've paused it, so essentially, you can use driver's licenses in your Google Wallet for zero knowledge statements. You can also use ID Pass, which is a way to hold any US passport or UK passport to the back of your phone and have that essentially read in a secure way and sort of a credential issued to your phone based on those passports, etc. And you can make zero knowledge proofs from those in Google Wallet. Now it's being rolled out, so I'm not sure it's on your Android phone today, but it is being used today in some on some websites, and in particular, there's one flow through Google you can use it with. As for your question about using it in like the Singapore wallet, I would love to work with whoever's there to get this to work with Singapore. There are people in the Singapore Google office who I can put you in touch with, and we'd love to do a trial for any sort of digital credential in Singapore. This technology works for those MDocs, which are those ISO standard identity documents, and it also works with JSON web tokens and so forth. I hope. Did that answer your question? Here, I'll show you the rest of the
So if we're interested
video
in just following up on your work specifically and so on, are there paper links? Are there GitHub repos? How do I follow up to say, hey, I'm interested in using your techniques?
Okay, so yes, our code is open sourced. So you can go, it's called Longfellow ZK, and it's available. Anybody can use it. It's several other open source wallets have used it already. We have a ePrint paper that's linked from there, and we have this work that's been externally audited by two security firms to make sure that the implementation corresponds to the protocol and the protocol itself is sound. We're also working on a formal verification of that, etc. Probably if you want to actually use this, please reach out to me. My email is just shelat@google.com or abhi@northeastern.edu. And so either of those work, please reach out to me. I would put you in connection to the right people to do whatever trial or pilot if you are interested in using this in any sort of trial or scheme or deployment at scale. It's essentially free to use. We work with groups to make it possible.
Fantastic. Thank you so much.
It's one of the nice, yeah, go ahead.
No, I was just saying thank you. Thank you very much.
Sorry that I couldn't make it there. My health is not great, and I couldn't fly there this week. But I'm very sorry to miss the conference and to miss the company there. But feel free to reach out to me if you're interested in this, and if you have any technical questions about that as well.
Turn it off. I turned it off. Sorry.
Great. Yeah. I can't hear it though. Can you say it again?
Just a minute.
Hello. So I'm Vineet on this side. A quick follow-up on the Google Wallet example that we were showing. Is the proof being generated on the client-side device, or is it being generated on the Google servers?
Oh, no. This the proof is being generated on the phone. The whole mechanism here is for user privacy, and essentially as I was, let's see, the very first mechanism here is that the whole principle here is that it's only you, your user. This is the flow right here. This diagram. After the credential has been issued to your phone, the only communication goes between your user device and the relying party. Now, so the ZK proof, and in the video that I was showing there, which maybe it didn't finish the video, the proof is being produced on the phone and is being sent from the phone to the relying party. The relying party website is basically verifying it and then essentially continuing on.
So just
Does that make sense?
yeah,
It's
it
very
makes sense.
critical that there's
So-
no phoning home, no Google servers involved, and no, the issuer is not involved in this flow.
So
Because again, we don't want to leak the metadata of who you are connecting with and when you connect with them.
yeah, great. So so would there be any hardware requirements of the on the prover side? Like, so if I'm generating on the client device, how powerful the client device? Can it be generated on a mobile, or do you require some like more memory or more proving time, so on, or it's possible even on?
Yes. Yes. So this is possible. The whole point is that it's possible. Do you still see my slides?
Yes.
Or?
Yeah, yeah.
Yeah. So the whole principle is that the proof is creatable on the phone, and it takes about 800 milliseconds on a Pixel 6 and about 300 milliseconds on an iPhone 15. So the proof generation is not the bottleneck. Let me show you that full video again. Where is it? Right here. So just to explain what's happening, this is a test website, and the website is requesting the credential, and it uses the same mechanism that passkey uses in order to connect with your phone. So your phone, basically, you scan this QR code. If you're doing this from your phone, of course, it happens all natively on your phone, but this is kind of the hardest use case across device. You select which wallet. This is, if you have more than one wallet on your phone, you can essentially use either of them. Google Wallet now basically confirms this is the information that you're going to share, your birth date. In this case, it's whatever the example is asked for the birthday, not age over 18. It shows you which website you're going to share it with. And then once you agree, it asks you to do a biometric motion right here. You have to basically open the secure element, which with your fingerprint. That produces the signature on that transcript that's being sent. And now essentially, in the time that it takes to connect Bluetooth connection between the phone and the website, it has produced the phone, it has produced the proof and uploaded it, and it's already sent to the website there. You see that the proof is about a 400 kilobyte proof that's been sent and processed by the relying party website.
Okay, great. Thank you.
Yeah, this demo is also several months old. So again, as I mentioned, the proof system has improved, but again, the latency is not in the generation of the proof. Now it's basically in human factors like you touching your screen.
Thank you, Abhi. From the audience, is there any more questions? Yeah, if not, then yeah, thank you, Abhi, for joining into the call and for that insightful session on the modern credential.